Hi everyone, I'm Daehyeok Kim. I'm a fourth year PhD student at Carnegie Mellon. In this talk, I'm going to introduce our system called T, which enables to build data-intensive network functions and programmable switches. This is a joint work with my collaborators at Intel, ByteDance, and my advisors at CMU. To give you a context of this work, network functions are an essential component in data center and enterprise networks. Examples of network functions include load balancer, firewall, and network address translators. They are typically deployed on a critical path of the network, so their packet processing performance and scalability are critical for overall network operations. Today, there are three typical options to deploy network functions. The most traditional approach is to use standalone middle-box appliances. In this option, each device is dedicated to a specific function. And the second approach is to implement NFs on a cluster of commodity servers, and this approach is also called Network Function Virtualization, or NFV. Since each function is just an application running on server, it's easily programmable, and it's generally more cost-efficient than standalone hardware. More recently, with advances of programmable switch ASICs, we can also implement some types of network functions on programmable switches. With their capability of line-rate packet processing, network functions running on the switches can easily process very high traffic rate. As you can see here, since each option has different characteristics in terms of performance, memory, and price, network operators may choose a proper option based on their target workloads and operating conditions. However, we observed that none of these options can serve very demanding traffic workload in a cloud setting. An example of such demanding workload would be a workload that consists of tens of millions of concurrent flows with a terabit per second traffic rate. To serve such workload, since we need a very large number of instances of standalone hardware devices or commodity servers, both options are not cost and energy efficient. In contrast, since a single programmable switch can process very high traffic rate, it seems promising for this workload. However, unfortunately, it cannot maintain necessary flow state for the large number of flows. And the key reason for this is limited SRAM space on the switch, which is tens of megabytes. Because of this limitation, as mentioned earlier, it's infeasible to maintain large state. For example, load balancing state for 10 million flows requires around hundreds of megabytes, which does not fit into on-chip SRAM. You can think of just adding more SRAM as a solution for this, but it's not cost efficient because SRAM is generally very expensive. So in this work, we try to address this problem by answering this question. Instead of adding expensive and unlimited amount of SRAM to the switch, can we leverage larger and cheaper external DRAM that already exists near the switch ASIC? Actually, there are two places where we can actually find available DRAM near the switch ASIC. The first one is in the switch control plane. The ASIC and the control plane are on the same switching board. The control plane is a typically server equipped with a CPU and a few gigabytes of DRAM. The ASIC can access DRAM through a PCIe bus, which can support at most 1 or 2 billion operations per second. This is much lower throughput than the data plane's packet processing speed, which is a few billions of packets per second. And in general, it's hard to add more DRAM and extend the bandwidth without significant hardware modification or improvement, which results in limited scalability. There's another option, which is onboard off-chip DRAM. Some switch chip vendor provides some amount of DRAM as an extension of the ASIC. In such designs, a dedicated portion of ASIC chip needs to be consumed for accessing DRAM, and access bandwidth and size are fixed at the chip design time, which limits scalability, same as the control plane option. Also, since it could enlarge the switch chip size by adding additional component, it can increase the overall operational cost. Fortunately, we found another opportunity outside the switch, which is a bunch of DRAM available on servers connected to the switch. So if we can somehow utilize those DRAM on servers to store large lookup tables, it could be a solution that provides scalable memory size and bandwidth at a lower cost, since it just uses existing switches and servers in the network. To realize this vision in this work, we developed table extension architecture, or T, for programmable switches. Essentially, T provides network functions with a virtual table abstraction that creates an illusion of large lookup table using external DRAM on servers. And T provides an APIs that allow developers to easily enable T in their NF implementations. It also provides low and predictable lookup latency with scalable throughput. Now, let's take a look at a key design component of T. At a high level, to use T, developers implement their NFs with T API in P4. Then they can compile it with an unmodified P4 compiler, which keeps them with binary loaded to the ASIC. At runtime, while the NF running on the ASIC processes packet as usual, T allows it to access lookup tables from either on-chip SRAM or external DRAM on servers. While this idea of using external DRAM sounds simple, we had to address several challenges to realize our vision. When a packet comes into the pipeline and there's no entry for the packet in SRAM, the ASIC needs to access the table on the server. To achieve this, the ASIC can access DRAM through the control plane, so CPUs on the control plane and the server establishes a connection, and the control plane CPU retrieves the entry from DRAM through a traditional RPC-like mechanism. But in this control plane-based mechanism, due to CPU involvement of the control plane and the server, it can include high and unpredictable latencies, and also excess bandwidth between the ASIC and the control plane as well as the control plane and the server is limited. So we need to design DRAM access channel that enables direct memory access from ASICs without involving the CPUs and also without hardware modifications. Once the ASIC can access the external DRAM, the next step is to locate and access the correct table entry for a given key, such as 5 tuple of a packet. However, as you'll see later, just using traditional hashing schemes designed for table lookups for SRAM in a switch board could require multiple memory accesses, which can result in high and unpredictable latencies. So what you really need to achieve is to retrieve a correct table entry in a single memory access. Another critical feature that T must provide is deferred packet processing, which means that during the table lookups using external DRAM, it needs to somehow hold the packet so that after the lookup completes, it can use the retrieved table entry for processing that packet. If we just naively buffer the packet at the switch, it can consume an excessive amount of switch's packet buffer, which is undesirable. So we need to enable deferred packet processing without stalling the entire pipeline and consuming a large amount of switch resources. Another challenge is about scaling the system. With a single server, memory access bandwidth and availability can be limited. While we can achieve higher throughput and availability using multiple servers, we observed that there are a few challenges we need to address to utilize them effectively. In particular, when there are multiple servers, we need to balance the access loads across servers so that we can avoid a situation where only a few servers are overloaded. Also, we need to deal with servers' availability changes fast to minimize the performance degradations. Now I'll describe how we address these challenges in designing T. As mentioned earlier, the ASIC needs the capability of accessing external DRAM directly, which is normally not supported by ASICs today. Can we enable ASICs to access external DRAM without hardware modifications and CPU environment? We designed the memory access channel based on RDMA, which provides an remote memory access capability with low and predictable latencies. And in particular, we leverage programmability of the ASIC to craft RDMA requests on demand. Let me explain how it works. When a packet comes into the switch ASIC pipeline, the ASIC adds RDMA protocol headers to craft RDMA write or read request. Then the server NIC will respond it with an RDMA response packet. Then the ASIC can parse the response as a normal packet. Also, to prevent possible RDMA request loss at the NIC, we employ a simple switch side flow control without implementing a full stack of RDMA functionality. With the memory access capability, now we have to think about how to use it for actual table lookups. Although our RDMA-based channel provides a low and predictable latencies, it still takes around 2 microseconds. So if a table lookup operation involves multiple memory accesses, it could result in high and unpredictable latencies. So our question is, can we devise a table lookup mechanism that takes a most single round trip or support constant time lookup complexity? The most common solution used for constant time table lookup within a switch hardware is cuckoo hashing. So we started from cuckoo hashing as a potential solution, and here let's see how it would work in our context. In a two-way cuckoo hashing, for example, when you look up an entry with a key, there are two candidate buckets where the value for the key can be located, which means it requires two memory accesses to retrieve the correct table entry. However, while SRAM in a switch supports parallel memory accesses for such table lookups, it is hard to support it on DRAM, especially through a RDMA channel efficiently. So we need an alternative that can enable table lookup with a single memory access. To this end, we devised our data structure called T-table, which designed based on prior work called bounded linear proving, or BLP. BLP was originally designed for improving cache hit rate in software switch, and we repurposed its way of placing buckets for a given key in a hash table. Unlike traditional cuckoo hashing, BLP puts two buckets in consecutive memory regions. To do so, it trades some amount of space efficiency for contiguous bucket allocation, which works well for our needs. This contiguous allocation allows us to retrieve two buckets in a single RDMA read. Then the ASIC can parse entries in those two buckets. Also, it significantly simplifies our insertion and deletion logic as well. One key distinction from the original usage of BLP is that while the BLP is originally designed for caching, in our design, we ensured that the T-table, which uses BLP, keeps the entire entries, and let on-chip SRAM keeps just a small portion of them as a cache. Now, while the ASIC can do table lookups with our T-table structure, the ASIC must be able to process packets with retrieved table entries such as an address mapping in NAT. It means that packet processing needs to be deferred until a lookup completes for the packet. And the key question here is, can we defer only a packet corresponding to the lookup without stalling the entire pipeline or buffering it at the switch? To solve this problem, we devised a way to offload packet store to T-table, which enables asynchronous packet processing. It consists of two ideas. First, instead of buffering packets at the switch, we employ scratchpad in T-table to store packets by augmenting the original data structure. So when the ASIC needs a table lookup, it first issues an RDMA write to store the packet to the scratchpad, and then issue an RDMA read to read the original packet back together with two buckets. While with this method, the ASIC can retrieve both buckets and the original packet, it has one problem, which is due to the current ASIC's hardware limitation, the original packet and the second bucket cannot be parsed very efficiently. So we revised our table structure with a shadow table, which puts a copy of the second bucket between the first bucket and the original packet as shown in this figure. It slightly increases DRAM usage, but it works fine because in our scenario, there's enough space in DRAM. With this new data structure, the ASIC now can parse two buckets and process the packet with the retrieved table entry. So far, I've explained a basic design of T with a single server. As mentioned earlier, we could improve the performance and availability with multiple servers, but there are some challenges. So here I'll just briefly mention our high-level ideas to address them, and please refer to our paper for more details. The first idea is to balance memory access loads across multiple servers as well as scale out the throughput. We employ a small on-chip cache which contains a few of frequently accessed table entries. The second idea is to react servers availability changes fast. We repurpose ASIC's capabilities, including event-based packet generation and meter. Putting it all together, T provides a virtual table abstraction to NFs so that they can have an illusion of large lookup tables. We leverage ASIC's programmability to enable external DRAM access purely in the data plane, and repurpose VLP to devise an efficient table data structure that allows table lookups in a single round trip. Also, by offloading the packet store to T table, we enable asynchronous packet processing. Lastly, we employ a small on-chip cache to support higher throughput and for better utilization of multiple servers. Let me close with our implementation and a few performance results of T. We implement T, API, and runtime as modules in P4 so that developers can easily enable T with their NF implementations. Using APIs, we implement canonical NFs, including NAT, stateful firewall, and load balancer. We evaluate T using a testbed consisting of a Tofino-based programmable switch and a number of servers with RDMA NICs. Our first question is, can T provide low and predictable lookup latency? We measured the lookup latency with different original packet sizes and compared it with the server-to-server RDMA performance. Here, x-axis is the packet sizes and y-axis is the lookup latency in microseconds. This research shows that T can achieve around 2 microseconds latency, which is slightly higher than that of server-to-server read, RDMA read, and T incurs this small overhead because original packets are piggybacked to each RDMA packet. Also, this error bar indicates 99th percentile latency, which shows T can provide predictable latencies. And then our next question is, how does T affect processing latency of network functions? To evaluate this, we measured the distribution of per packet processing latency of NAT by using a set of packet traces, including both synthetic and real traces. For synthetic ones, we generate traces with different flow size skewness because it can affect the cache hit rate and latency distribution. And we compare it against the baseline, which only uses switches SRAM without accessing external DRAM. Here, the x-axis is the latency and y-axis represent the CDF of the latency. This is the distribution of the baseline's latency, which takes a few hundreds of nanoseconds. And this is the result for T-enabled NAT. Basically, the distribution is divided into two parts. The left-hand side is the distribution when lookups are served by on-chip cache, and the right-hand side represents the case where lookups are served by T-table on external DRAM. We can see that for more skewed traces, they have higher chances of being served by on-chip cache. Also, regardless of the skewness, we can see that the variance is small, which results in the predictable end-to-end latency. Lastly, we also measure the throughput that T-enabled network function can support with a different number of servers. And again, we use T-enabled NAT as an example. Here, x-axis is the number of DRAM servers, and y-axis is the throughput in million lookups per second. We can see here that the throughput can be scaled by adding more servers, and also we can see that the on-chip cache actually helps improve the throughput a lot. And the reason why the case with 8 servers cannot achieve higher throughput is that it is actually capped by our traffic generation rate in our testbed, which is around 138 million packets per second. We also have some other research in the paper, including cost efficiency compared to server-based implementations, performance during failover, and switch ASIC resource usage. To conclude the talk, limited on-chip memory has been a roadblock for adopting switch-based network functions, especially for demanding workload. To solve this problem, today I introduced T that provides a virtual table abstraction for NFs, and we realize it with 4 key ideas. We show that it provides low and predictable lookup latency with scalable throughput for various network functions. With that, I'll end my talk. Thank you for listening.